I am Anuradha Mathur. I teach physics at Modern School Vasant Vihar, New Delhi. Today we will be talking about magnetism. Moving charges and electric currents are associated with magnetic field, a fact that was discovered in early 19th century by Ampere, Oersted, Boyd-Sawatz amongst others. Magnets have a special property. They have a field associated with it. Electric currents give the same property. This connection we will make and try and learn some properties of magnets and solenoids, compare the two, and thereafter find a solution and find the magnetic field due to a bar magnet along its axial line and along the equatorial line. Some basic properties of magnets are that earth behaves like a magnet and it has its field directed from the south, geographic south towards the north. If you have a freely suspended magnet like this compass needle, the end that points towards the north pole is called the north and the south seeking pole is called the south. Like poles of a magnet repel each other and unlike poles attract. There is a field around a magnet or space around a magnet where its influence can be felt. You might have done these experiments earlier, where you just sprinkle some iron filings onto a magnet and observe its pattern. This pattern is because there is a region of influence. It creates a pattern showing that there is a field around it, a region of influence, so to say. This field is three-dimensional in nature and therefore, you could talk about the magnetic field at a distance away from the magnet as well, which means that there should be some rules, some laws that will govern the magnitude of this field. Because current is associated with magnetic field, we have talked about magnetic moment, which in turn is given by m. The magnetic moment is equal to the current flowing through a loop into the area vector. The area vector becomes important because if the direction of current in the loop changes, then the area vector, which is the line perpendicular to the plane of the loop, is going to point in this direction and this gives us the field pointing upwards. If you change the direction of current in the same loop, then the field would point in the opposite direction. This result shows that this is a vector quantity and so is this a vector quantity. If you were to increase the number of loops, then this would include the number of loops over there. We can take this idea from here and use it to calculate the magnetic field due to a bar magnet along two lines, one along its axis and along the line which is perpendicular to this axis. What will be the magnetic field at this location or at this one? In order to do that, I have over here an experiment which shows you the magnetic field lines because of a magnet and the field lines that are produced by a solenoid. In order to find the magnetic field due to this bar magnet along its axis, any point around here or on the equatorial line, we have over here an apparatus by which you can see the field lines due to the bar magnet and the solenoid being almost the same. These are the closed loops starting here, going all the way through the magnet. In this case also, from this end of the solenoid right around here and going all along the solenoid this way. So, closed loops which represent the field lines of a magnet are seen in these two, which are identical. You must know that the electric field lines and the magnetic field lines are different. In the case of electric field, the field lines originated from the positive charge and end at the negative. In this case, they are continuous loops. So, the field appears to be within the setup, within the magnet, within this solenoid and different from an electric field. Now, let us see. In order to calculate, let us make a picture of this solenoid. Say I represent it by this cylinder. Say the area of cross section is given in terms of the radius of this solenoid. It is a uniform radius solenoid. Say A is its radius. Say the length of the solenoid is 2L, and along here I want to find the field at this point P. This is its center. So, L from the center here and likewise. So, let us say the distance of this point from this central point here is some value r, and we want the field. So, let us imagine a small element somewhere around here like this, which would be my dx, and say it is at a distance of x from the center of the solenoid. Now, if you take this into account, you will use your Boyd-Savart's law to give you the value for delta B on account of this current element which I have just colored. This will be equal to mu 0, the permeability here, into the current that is flowing through it, into the area square upon your 2 into r minus x the whole square plus a square, and the whole thing raised to the power of 3 by 2. Now, from here, if you were to find for the whole solenoid, then you would have to integrate it. So, the total field would be this, which would be mu naught I, we have left out the dx. So, dx should also be included, mu naught I into your a square upon 2, and if there are n turns per unit length, then you will account for that factor as well. And from minus L to plus L, from the center minus L would be this and this would be plus L, and this value, and all the way the denominator remains the same, r minus x the whole square plus a square raised to 3 by 2. This expression can be made as an approximation, and what is the approximation? That this point that we are selecting is at a distance which is much larger than the length of the magnet, as also the element that we considered for our solenoid is going to be very close to the center. So, our x value is very much less than r, and so is our L value less than r. So, we now get this expression B is equal to mu naught n I being the total number of turns, and I the current, a square upon 2 r cube. We had already talked about the magnetic moment being equal to the number of turns, which is n into 2L, current flowing through the loop, and the area vector. This can be, the formula can be now written for B in terms of magnetic moment as mu naught 2 m upon 4 pi r cube. If you are to relate this value for the magnetic intensity with that of an electric dipole, you can then say that the value along the equatorial line would be exactly half of this. Now, you may argue, how can you take such a suggestion which is just talking in terms of two dipoles being the same? Well, if a dipole behaves in a particular way, other dipole should also behave much the same way. That is the reason why we are taking electric dipole value that we had obtained here mathematically to give us the value for magnetic field value, and you can write then half of this value will have just this. So, this becomes our magnetic field along the axial line, and this becomes the magnetic field along the equatorial line. Something very easy and simple. Some of the books and some people still argue that you should be talking about pole strength, but pole strength is no longer an option to talk about, because we are now going to be talking only in terms of magnetic current loops, electric current loops, and their associated magnetic dipoles. Therefore, all magnets are going to be treated as though made up of a large number of current loops, as we have just done. We can approximate this formula, and how is that? Because we can say that the distance r that we have selected is much larger than the length of the magnet. Also, the element that we have chosen to give us the value for B is very close to the center. So, our x value is also small as compared to r. Doing that, we are then going to get the formula as the magnetic field B to be equal to mu naught n into I 2 L A square divided by 2 r cube. Now, if I want to reduce or accommodate and adjust magnetic moment idea and the concept of magnetic moment idea, then m, as we had discussed earlier, is equal to the total number of turns multiplied by the value for current flowing through it into the area vector, which is pi a square. Using this m value in this expression, B along this line at the axial point, as we have calculated that, will become mu naught 2 m upon 4 pi r cube. This expression also is going to be very useful, because now what we are going to say is that if this magnetic dipole has the magnetic field value given by B along the axial line by this expression, if I relate it to an electric dipole, I can then predict the value along the equatorial line, which will be half of the value. Now, you may say that how can you just pick upon electric dipole and say that all right, just because electric dipole had this value, magnetic dipole should also have it. But you must always remember that all dipoles are going to have much of their fields in the same way or the same pattern, and that is why you can conveniently predict the value of magnetic field along the equatorial line to be equal to exactly half of that it is on the axial line. So, your value then becomes B is equal to mu naught m upon 4 pi r cube. Many books, many people argue that you should be giving the value of magnetic pole strength. Well, we are never going to be talking about a pole strength for a magnet, because now we are associating all magnetic fields to current loops, and therefore, it is always convenient and easy to say that a bar magnet also has circulating current loops, and therefore, by association, as we have calculated right now, you can always find the value for magnetic field from the center of the magnet. I have a magnet here and I cut it into half. So, what will be the magnetic field because of each of them? From our expression that we have just derived, we can see that the magnetic moment, the value for L will become half, and so each of them will have almost half the strength. This you can check by using a magnetic needle or a magnetometer disc. You can check this value to be becoming almost half of it. Supposing I were to cut the magnet into half like this. So, now I have two long magnets. What will be the pole strength in this case? Very interesting, because now our solenoid that we had with a radius of A will have a radius of A by 2. So, the field would become almost a quarter of what it is right now. Very simple and very interesting. So, you can do more calculations like this using this expression, answer all the typical questions that are asked about bar magnet, typically why can't you have a monopole, etc. So, from today's lesson we will conclude, and you have learned that magnetic properties, basic magnetic properties of a bar magnet, and you have used a solenoid and concept of magnetic moment associated with a current loop, and found the value for magnetic field intensity at a location along the axis of a magnet, and so also along the equatorial line of a magnet.